All right. I'm going to talk about stock assessments today. In particular, I'm going to talk to you guys about how do they work in terms of what data goes into them and what data comes out of them from kind of a high level, hopefully accessible point of view. And then finish up talking about the projections, which are sort of a component of the stock assessment that basically takes that stock assessment and turns it into management changes or management advice. So, first of all, obviously, there's not just one single sort of stock assessment. There's really a whole range of different models, different approaches that we use to assess species. And it really is based on kind of the quality of the data. We can usually divide them into sort of data poor and data rich stocks and stock assessment models. It's really more of a spectrum as opposed to two categories. But today I'm going to be focusing on kind of this data-rich corner here because this is going to be where a lot of the species that you're probably familiar with are assessed. This far dark blue point of the arrow is that ecological reference point stuff that we were talking about this morning. This is maybe a step or two back in terms of the kinds of data that we need to get good answers out of these assessments. What kind of data goes into the stock assessment? What makes this data rich? There's two key pieces of information we need for these models. First of all, we need catch. We need to know how many fish did we kill. And this comes obviously from your harvest. How many fish did you kill and bring back to dock, your landed fish? But we also need information on discards, those fish that are thrown back dead at sea and never make it back to the dock or the dealer. And those release mortalities, those fish that are released alive but die because of the stress or the injury of being caught. All of that contributes to the total mortality, the total number of deaths that this stock is experiencing. And obviously we need this from both commercial and recreational data. So commercial data, we get this information from dealer reports, trip tickets, VTR reports. We have dedicated observer programs where we send people out to sample boats, watch them fishing to see what they're discarding. And of course, the MRIP data is what gives us our recreational data. And so for MRIP, we have both components combined. We have both the harvest and kind of that discard or release mortality in MRIP together. So we need to know, number one, how many fish did we kill last year and every single year in the past? And then number two, we need some kind of index of relative abundance from a survey. And this is because catch goes up and down for a lot of reasons. So catch alone, or how many fish did we kill, is not enough to tell you if the stock is in a good place or a bad place. So the catch can go up or down because the population goes up or down. We caught more striped bass last year because there were more striped bass out there, or we caught fewer because there were fewer. But we also catch more or less because regulations change. You put in a quota or you loosen up that size limit. Effort changes. People take more trips, or the price of fuel goes up and people take less trips. People get better at fishing for these species. Everybody's got a fish finder on their boat now, and they didn't have that 20 years ago. So we need a way to separate out population effects from these effort or regulation effects. And that's where this population index or this survey, this fishery independent survey idea comes in. So basically, scientists go out and catch fish every year using the same methods, the same area, same time of year, doing everything exactly the same way. And we can't count every fish out there when we do this. But instead, we can tell from year to year if the population is going up or going down. So if you go out there and you tow that net 50 times, on average, how many fish did you catch? And is that higher or lower than last year and the year before and 10 years ago? This gives you what we call an index of relative abundance. So it's not total abundance. It's not how many fish are out there altogether. It's what's that population doing. So that population index is providing the trend of the population. Is it going up? Is it going down? Is it staying stable? How is it changing over time? And the catch is providing the scale of the population. How big is it in absolute numbers or absolute weight? And so let's do a real super simplified example so I can show you what I mean and how these two pieces of information come together. Let's say we do a survey. We go out, we tow that net a bunch of times, and we get, on average, 50 fish per tow. Let's say 50 bluefish per tow. We open the season up, and we catch 3,000 pounds of fish. we do the survey again, and this time we tow the net a bunch of times, but we only catch 25 bluefish per tow. How large was the population when we opened the season? Well, what we can tell from this combination of information is that when we removed 3,000 pounds of fish from the population, the index declined by 50%, by half. So we took 3,000 pounds out, and now the population is only half as big as it was at the start of the season. So that tells us that at the start of the season, the population was 6,000 pounds. So this is essentially what our stock assessment models are doing, is that we're looking at trends in index data and trying to figure out how the catch drove that trend. So this is important because for our conversation about calibrating data and the importance of the scale of these numbers, because catch is what's providing that scale of the population. How big is it in absolute numbers, in absolute weight? So if your catch is wrong, the scale of the population from your assessment will be wrong. The trend is probably going to be right, but the scale is going to be wrong. And what we see is this usually leads to, maybe unintuitively, higher catch rates equal a higher population size. So when we recalibrated all that MRIP data, you probably saw that population go up. We think now we realize there's more fish out there than we thought because we were killing more of them than we thought, but the population trends stayed the same. So basically what that's saying is you need more need more fish in the water to sustain that level of catch and still see that trend that we saw from the index data from the catch at age over time. So obviously this is a really simplified example, right? And you're probably sitting here thinking about, well, you know, that population index declined, but those fish are dying from natural causes, right? It's not just fishing mortality. And that's true. And so we also need other sources of input data. A big one is biological information, like what % of that population is dying every year from natural causes. If we know that from biological studies, then we can account for that. So that index goes down, and some of that's fishing, and some of that's natural mortality. You can combine them to scale that population up to get both components. We also want to know how fast the fish are growing. When do they mature? Other sources of information about the life history or the biology of the species. And we get this data from state, federal, and academic research projects and surveys, and also from citizen science. So things like tag reporting, participating in these tag programs gives us important information about growth or movement. And some states have freezer programs where you can donate the rack of your fish after you filleted it so that we can get the otolith and the size of the fish to figure out how old it is and how big it is. We also need information not just on total catch. Total catch is great and it's really helpful, but catch at age is even better. So how many fish of each age do we kill every year? So you can follow that fish that starts out at age 1 and watch them go through the population. How many are we killing at age 2, at age 3, at age 4, to see what happens to that cohort over time. And to do that, we usually need length samples from the landed fish that we combine with that other age data that we collect from other programs. MRIP gives us the length data for our measured fish that are brought back to the dock. And we have state and federal port agents doing the same thing for the commercial fish. So they go out there and measure the commercial fish that we are killing. We also have observer programs that measure the commercial discard lengths. And citizen science is one of our most important sources of logbook programs, for example, for recreational release length. So if you're looking to participate in the stock assessment process, these kind of volunteer angler logbook programs for the sizes of released fish is really important to our assessments. So that's the kind of information that goes into the stock assessment. What kind of information are we getting out of the stock assessment? First of all, we're getting fishing mortality. So what proportion of the population is dying every year due to fishing? And second of all, population size. So we see this, we report this sometimes in terms of total numbers of fish, but more commonly you're going to see it in terms of spawning stock biomass, or SSB. So the biomass of mature fish in the population. And we care about that as opposed to just total biomass, because what we really care about is that biomass, or that number of fish that are out there that can spawn and contribute to the next generation of the population. So the other part that we get out of this is stock status. So if I tell you F is 0.3 and there's 30,000 metric tons of spawning stock biomass out there, is that good or bad? Well, it depends, right? It depends on the species that you're talking about. So we need to know not just what the level is, but are we fishing too much? Are there enough mature fish in the population? And so we compare stock status, or compare these F and SSB estimates to reference points to figure out if we're overfishing. That is, if F, or fishing mortality, is too high, we're removing fish faster than the population can replace them, and that's bad. If the population is overfished, if SSB is too low, we run the risk of what we call recruitment failure. That is, not having enough eggs produced to sustain the population into the future, and that's also bad. So this is sort of the results, or the stock status that we get out in the end. So we've done our stock assessment. We know where we are now. That's our stock status. And we know what happened in the past. That's that sort of timeline of SSB and F over time. What do we do next? What do we do into the future? And that's where these projections come in. So here in this situation, I'm showing a graph of some example output where you can see we're overfished. That is, that SSB is below that threshold, and where overfishing is occurring, so F is above that threshold, which means we need to do something to help the population recover. So what we do is basically run projections. That is, we take where we are in that last year and project forward, or we predict what will happen to the population in the future under different levels of catch. This incorporates uncertainty about a bunch of different things. So we haven't really talked about uncertainty here yet, but projections are really where they come into play. I've showed you that graph with the lines, and as if it's a single line, as if there's one single value. That F is 0.3 in that last year. But really what comes out of the model is we say F is most likely to be 0.3. Maybe it's a little higher, maybe it's a little lower. And that uncertainty comes from things like the uncertainty in the catch data. So we say, here's how much catch we caught, or we think we caught. Maybe it's a little higher, maybe it's a little lower. For some species, we're really good at that. For other species, there's more uncertainty. And so we say, here's the index data. Maybe it's a little noisy. Maybe there's multiple indices, and they go up a little bit or they go down a little bit. They went up 10%, but maybe it's plus or minus. And so the model sort of sorts through all those different sources of uncertainty and says, okay, here's the best answer. Maybe it's a little higher, maybe it's a little lower. And so we start from that point, from that uncertainty, and project the population forward. So population size in the most recent year is 30,000 metric tons. Maybe it's a little higher, maybe it's a little lower. Let's try searching over that whole range. We don't know what future recruitment's going to be, so we incorporate that uncertainty into there, as well as other factors that are important for different species. So these projections come out, and they're providing the probability of being above or below your reference point under different scenarios. So we don't give you necessarily a single answer. We give you sort of a probability about what's most likely to happen in the future. So this, for example, is something you might see. Here's our F estimates coming out of the stock assessment. I cut that time series off, and you can see in black, that's what the stock assessment said was happening. And then in blue, we're projecting forward under, we've reduced catch, and so that F is coming down, but it's coming down with some uncertainty. That's actually probably really hard to see on this screen, sorry. But basically, you can see at the beginning, we've got 100% chance of F being above the F threshold in 2017. So overfishing is definitely occurring. Maybe it's not exactly 0.3, maybe it's a little higher, maybe it's a little lower, but it's definitely overfishing. We reduce the catch, and then in this 2020, we have a 50% chance of being above the F threshold in 2020. So if we catch at, let's say we reduce the catch by 18%, then we've got a 50% chance of being above that threshold, and we've got a 50% chance of being below that threshold in that last year. So we can put in 50%, you're probably thinking, that seems a little high. 50% chance of overfishing? We have a hard time gauging this catch anyway. And that's true, and that's why a lot of times we'll put in buffers around this. So we'll say, here's what catch we need to get a 50% chance of not overfishing. Let's ease back, let's put in a little buffer, aim a little lower, so that even if we miss it, with our monitoring, we will still have a lower risk of overfishing. That's and then the cycle continues. We go from data collection to stock assessment to management changes through those projections. We set a new management regime, and then we go back to the data collection part to see if we're meeting that management regime, if we're hitting that target, and then how is that affecting the stock going forward. So the cycle continues. So thanks, and I'm happy to take questions now.